Chapter 6, Introduction to Uniform Circular Motion and Gravitation. So here's a race car going around a circular track, and it's kept on the road by friction, and these wheels are actually rolling without slipping, which is a really cool concept. So we're going to get back to kinematics, but now we're doing rotational kinematics. So remember we had position, velocity, and acceleration were the kinematic variables way back in chapter 2, I think. Well, now we're going to do the same thing, but now with angular position, angular velocity, and angular acceleration. So if you imagine this disk and it's turning, it might turn a certain angle. So it's just free to rotate around its axis, which is in and out of the page here. But how much it turns is given by an angle, theta. And if you take a point on the edge of the disk and ask how far it goes, it's this distance delta s, it's called the arc length, and there is an equation which gives delta theta equals delta s over r if the angle is measured in radians. So in this chapter is when we're going to start measuring angles in radians instead of degrees. So it turns out that 90 degrees is pi over 2 radians. Basically, a radian is about 57 degrees. But it's the way I remember the conversion, exact conversion, is 180 degrees, half a full circle, is equal to pi radians. And then the other thing is that this arc length is a function of radius. So if you're closer to the center, then you don't go as far, even if the angle is the same. I guess if you were right at the very center, you wouldn't travel any distance at all, even if the angle moved. So once you have angular position, you can now have angular velocity. The change in angular position divided by the change in time is this W. It's actually called omega. It's the last letter of the Greek alphabet. It looks like a curly W, but it's omega. Is angular velocity is delta theta divided by delta time. It's very similar to this old equation we have for velocity, was the change in position versus time. And actually, it turns out that the linear speed is equal to r times omega. So that's that, I guess, the speed, the tangential speed as it's going around in a circle. And here we have a car. You can imagine that it's got the wheel has some angular velocity. Well, the outside of the wheel will have some speed relative to the axle, r times omega, where again, omega has to be measured in radians per second for this to work. How fast does the car tire spin? If the car is traveling 15 meters per second, so that means the axle is traveling 15 meters per second relative to the road, I think that means that the outer edge of this tire is traveling 15 meters per second relative to the axle, so that as it's going backwards here, it's at rest relative to the road. So we'll talk a little more about that in class. It's called rolling without slipping. The linear speed of the rim of the tire is the same as the speed of the car. So you just solve for omega, 15 meters per second divided by the radius, and you get radians per second. Remember that change in velocity means there's a change in, there's an acceleration. So this is actually talking about if it's uniform circular motion, so the speed does not change, there's still an acceleration due to turning. So V1 and V2 are the same magnitude here, but they're a slightly different direction. So if you imagine taking both this green arrow and this green arrow off their trajectory, V1 is this direction and V2 is this direction. If you hook them up at the same, put their tails at the same place. So they're not the same vector, same magnitude, but different direction. So you would say that the velocity has changed by delta V. V1 plus the change in V equals V2. So the initial velocity, the change, and the final velocity here. So this change, delta V, is towards the center of circular motion, and that's going to give you some acceleration. Delta V divided by delta time is the acceleration, right? So this is called centripetal acceleration towards the center of circular motion. We call it A sub c, delta V over delta t. And they give you a sort of an argument in which they end up with an equation for centripetal acceleration is the speed squared divided by r. So what that means is the faster you're going for a certain radius circle, if you double your speed or something, you have 4 times as much centripetal acceleration going towards the center. And the R is on the bottom here. This means that if you have a larger circle but the same speed, it requires less acceleration to stay on the circular path. And they give a nice example here of a car going around a curve of radius 500 meters at a speed of 25 meters per second. So you see this a lot, curve of radius. So what they're saying is that anytime you're turning, you can kind of model it as being part of a circular path. Even if you're not driving on a circular path, some portion of that path could be kind of modeled with a circle that has some radius. So if you turn really sharply, that's a small radius of curvature. If you do a slow, like smooth turn, that's a large radius of curvature. So a lot of problems are worked out when they give the radius of the circular path. Even if it's not a circle out here or over here, for a small part of the path sort of tracks a circle. It talks about centrifuges, how they work to get sediment down to the bottom of a test tube, for example. Section 6.3 on centripetal force. So in the last section, 6.2, we learned about centripetal acceleration, A sub c, meaning that if you are going along a circular path, your velocity is constantly changing so that you are accelerating towards the center of that circular path, and the value of centripetal acceleration is v squared over r. Well, centripetal force is the net force required to give you centripetal acceleration. It's as simple as that. So this is really just a statement of Newton's second law, which is F net equals mass times acceleration. The acceleration in the case of uniform circular motion is v squared over r, and so the net force on an object traveling at a constant speed in a circular path is just m times v squared over r. It looks like this. Fc equals m times v squared over r. And another way of putting it is m times r times omega squared, where omega is equal to v divided by r. It's the angular velocity we talked about earlier. So again, here's something going on a circular path with a constant speed v. There is an inward force. If you go the same v but a smaller r, you need a larger force because you have a larger acceleration. Example 6.4 deals with figure 6.10. You're seeing a car from behind which is going on a horizontal circular path. So if you were to view it from above, you'd see a circle with a car going on that circular path, and it's over on the right-hand side of the circle. So the center of circular motion in this view here is just off to the left, and the whole circle is off to the left as well. And so since the direction of turning is to the left, the centripetal acceleration is to the left, so the net force must be to the left. The normal cancels the weight. There is no y component to the acceleration, but there is this leftward horizontal component, and that's given by the static friction. And you can, I guess, find out how fast you can turn without slipping by setting the static friction to be the maximum static friction when it's just about to slip. So that's what they do. Example 6.5 deals with banked curves. So now we have a similar situation, a car turning in a big horizontal circular path. So again, if you were to view it from above, you would see a big circle off to the left with the center of the center of the circle off to the left. But we are now viewing it from behind. So the whole circle is now just off to the left like a line. And so the acceleration is towards the center of a circular path. And what they've done is they've banked the pavement up at some angle theta. So what that means, sort of like a race track, as you're going around, the whole thing is tilted as viewed from behind. So now the normal force from the surface has a component towards the center of the circular path. And it has a component that's upwards. So the component that's upward is n cos theta. That will cancel out the weight because, once again, you're not accelerating up or down. And the component towards the left here is n sine theta. And if there's no friction, which I suppose it's possible that there might not be any friction, you can set n sine theta is this centripetal force, otherwise known as the net force. And so what they do in example 6.5 is they say, calculate the speed at which a 100-meter radius curve banked at 65 degrees should be driven if the road is frictionless. So once again, your force diagram does not include friction. It just includes normal force and weight, and that's it. And when you do that, you just set the net force, which is mv squared over r, to be n sine theta, that component towards the center of circular motion, and you balance the forces in the y direction. N cos theta is equal to the weight. And when you combine these two equations, you get this banking angle for a banked curve with no friction. The sine theta over the cos theta, which is like tan theta, is v squared divided by r or g, where these are dimensionless, I think, when you work this out. Section 6.4 is about fictitious forces and non-inertial frames. So here are two pictures of the same car. They're turning to the right, which you can kind of see by the wheels here. So there's a big circular path with the center of circular motion off to the right. This is a bird's eye view. And so the centripetal force is pushing the whole car to the right. However, this picture on this view A here is asking you to view life from the inside of this car and ignore the fact that this is an accelerating reference frame. So what you notice if you're sitting in that car is you would notice yourself being pulled towards the outside of the circular path. This is a fictitious force. It's called the centrifugal force, and it's exactly in the opposite direction of the centripetal force. So the centripetal force is F actual. That's the force needed to push you in the circular path. And I guess centrifugal force is a fictional force, which is if you don't know that you're in an accelerating reference frame, then it's a force that's coming from the fact that your body wants to continue in a straight line. And so since you feel like you're being pulled towards the outside. So there's a rotating frame of reference with this fictitious force, and there's the inertial reference frame for the merry-go-round, which is the actual lab frame. So this situation B is the way we do physics in this course. We set things up in the lab frame and have a centripetal force. But they're saying that there is a way of analyzing things in which we go to a rotating frame of reference, which is non-inertial, so Newton's laws don't apply, and you get this fictitious force. And it can be useful, for example, if you have a centrifuge with a test tube that is being rotated around in a circular path, there will be a centrifugal force on the particles pulling it towards the bottom of the test tube. And you can use this to settle platelets in a blood sample down to the bottom, for example. So even though it's fictitious, it feels very real if you're in an accelerating reference frame. And these next two figures, figure 6.15, is showing something called Coriolis force. So if you are on a rotating reference frame and moving, then there's another force, in addition to the centrifugal force, called Coriolis force, which turns your path in that reference frame. And in fact, this Coriolis force is what drives hurricanes. When you have a low pressure system and air moving towards the center of a hurricane, due to the fact that the Earth is rotating, then if you're in the northern hemisphere, you get a rightward deflection due to Coriolis force, and that's what causes hurricanes to always rotate counterclockwise in the northern hemisphere. But I want to go back to the bottom of section 6.3, where they have this PhET exploration called gravity in orbits, which shows a pretty nice exploration of a few things that are happening. So once a year, this is the Earth, which is going to be spinning once around its axis every day. So that's not, the spinning is not shown, but it's showing its orbit around the sun, this yellow thing. This is not to scale, but there's a yellow thing in the middle, which is the sun, and then there's the Earth going around once per year. And you can also add, we'll turn off the path here, you can add the moon. So as the Earth orbits the sun once per year, the moon orbits the Earth once per month. So it goes all the way around 12 times in its path as it goes, as the Earth goes around the sun. And we can zoom in on the Earth-Moon system, and there it is. We can put the path there of the moon, so that it's about every 29 days, the moon travels all the way around the Earth. And so all of these are circular paths, right? And so you need to have this gravity force. I think if you look really closely, you can see that the Earth actually shakes once a month as the moon orbits it, and this is what causes the tides to slosh around in the oceans. And that brings us to Newton's universal law of gravitation. So I guess this is a picture of Isaac Newton sitting under an apple tree, and he was thinking about, why does the Earth orbit the sun? Why does the moon orbit the Earth? There should be some inward pulling force, just as we had with the last couple of chapters. Anytime something's on a circular path, there's a centripetal force pulling it towards the center of that path. Well, he thought that could be gravity. An apple apparently fell on his head, and he thought, oh, maybe the gravity reaches all the way out into space and pulls the moon towards the Earth, and that's what causes it to orbit. So that's exactly correct. When this idea first came out, it wasn't widely accepted in England, but this astronomer, Émilie du Châtelet, was working in France, and she utilized calculus to explain gravity, which led to its greater acceptance. But the universal law of gravitation states that anytime you have two masses, there is an equal and opposite force attracting those two masses to each other. It's called F, and the equation for it, if you have mass little m and big M, is Gm times m divided by r squared. So here, capital G is a universal gravitational constant, 6.674 times 10 to the minus 11 newtons meters squared per kilogram squared. So then you have the two massive objects, both in kilograms, and the distance between the centers of those two objects are squared. So for example, when two 1 kilogram masses are separated by 1 meter, there will be an attractive force of 6.674 times 10 to the minus 11 newtons attracting them towards each other. Now that's very difficult to measure. It's an extraordinarily small force. We are unaware that even large objects like mountains exert a gravitational force on us. In fact, our body weight is the force of attraction of the entire Earth on us. And the entire Earth has a mass of 6 times 10 to the 24 kilograms. And we can say that the distance between us and the Earth is the distance between the center of us and the center of the Earth. And so that's always the radius of the Earth. So if you plug in capital G times the mass of the Earth divided by the radius of the Earth squared, lo and behold, you get 9.8. And the units turn out to be 9.8 meters per second squared. So that's exactly where the 9.8 comes from. It's actually a special case of this universal force law. When you have some little mass, little m, and your distance of 6,400 kilometers away from the center of a big mass of the Earth, then it'll be 9. You can shorten this equation as F equals little m times 9.8. And the reason it doesn't change much with r is because any little change in height doesn't much change the value of r sub e. It's always about 6,400 kilometers. But now that we have the more general equation, we can figure out, for example, what the force, the acceleration is of the moon. We can figure out how much the Earth wobbles as the moon goes around. This is what's causing the tide. Tides are caused by the fact that the gravity force from the moon varies with distance. So there is a stronger force of attraction of the near ocean to the moon than there is in the center of the Earth. So the entire Earth is pulled towards the moon with an acceleration which is due to the force on the Earth, but the ocean that's closer to the moon is pulled with a greater force, and so it accelerates a little more, so there's a bulge called a high tide at the side of the Earth that faces the moon. The opposite side of the Earth has a smaller force of attraction than the center of the Earth. So what happens with the opposite side is that the Earth is pulled away with a greater force, has greater acceleration than this opposing ocean. And so again, there's a high tide on the opposite side because it's left behind. It doesn't accelerate as much as the center of the Earth. So you end up with a high tide on the near side to the moon and the far side away from the moon. And as the Earth rotates once every 24 hours, there's a high tide where you happen to live once every 12 hours, as you probably know if you live near the ocean. Now, the sun also causes tides. So when the moon and the sun are in alignment, for example, at a new moon or at a full moon, this is called spring tide because you get an even higher tide than usual. When you have a first quarter moon or a third quarter moon, there's a right angle between the moon, which has a greater tidal effect because it's so much closer to the Earth than the sun, and so you get what's called neap tide. The tides don't go up as much during those moon phases. So tidal forces always have this tendency to stretch things. So, for example, as mass falls towards a black hole, it tends to get stretched out into these accretion disks. And lastly, this section talks about weightlessness and microgravity. So here is a collection of astronauts on board the International Space Station. And you can see they're not experiencing gravity. Their hair is flying around and they can just float around the ship. But what's interesting, in low Earth orbit, like at the International Space Station, there is a force of gravity on these astronauts. Weightlessness doesn't mean that the astronaut is not being acted upon by the gravitational force. Certainly, low Earth orbit's only about 300 kilometers up, and so they're only 300 kilometers farther from the center of the Earth than we are. So the force of gravity on these astronauts is only a tiny bit less. They're not in deep space. They're just above the Earth's atmosphere where there's no air resistance. So why do they feel weightless? It is because they are in free fall. If you were accelerating downwards in an elevator at 9.8 meters per second squared, you would feel weightless too. You'd be floating around the elevator until it crashed to the bottom of the pit. Well, what's happening with astronauts is that they're in orbit around the Earth, so they're continuously accelerating towards the center of the Earth at about 9.8 meters per second squared. A little less because the force of gravity on them is a little bit less than it is on the surface. But basically, it's not the lack of gravity that causes you to be weightless. It's the lack of normal force. It's the fact that they're in free fall. But once you are in free fall, you can do microgravity experiments. They have a Cavendish experiment, which can be done in space to measure capital G very precisely. And the last section of chapter 6 is about Kepler's laws of planetary motion. So basically what they're saying, there is an astronomer, old astronomer named Johannes Kepler, and if you look carefully at these dates, he died in 1630, whereas the Principia, published by Isaac Newton, that established the laws of gravity, was published in 1687, well after Kepler had died. So Kepler's laws of planetary motion were discovered before Isaac Newton laid down the principles for motion and gravity in the solar system. So they're kind of very empirical laws, meaning that people were looking at what the planets are doing and trying to describe what the planets are doing in their orbit around the sun. So the first law is the orbit of each planet about the sun is in the ellipse with the sun at one focus. This was something that was discovered by Kepler, who knew how to draw ellipses and knew how to draw planetary orbits based on the observations, and found this thing. It turns out if you have a mass and it's attracted towards this capital M, the orbit is not necessarily a circle, but can be, in general, an ellipse. Kepler's second law is that each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal times. So if it's close to the sun, it moves this area A1, which is equal to area A3 in an equal time that it moves out here. So what that means is that the planet is traveling slower when it's farther from the sun and faster when it's closer to the sun. Again, this turns out to be a direct consequence of the universal law of gravitation. And Kepler's third law states that the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distance from the sun. And again, it's an exact just consequence of the law of universal gravitation giving the centripetal force of orbits. So there are some examples. Here is where they derive Kepler's third law, which is the one that's pretty easy to derive. You set the net force equal to gmm over r squared, can solve out for the speed of a circular orbit, find out the period. If you know the speed and the radius, you can find the period, and the t squared equals some constant times r cubed. So anytime you take the ratio of two different planets, they'll have the same values of 4 times pi squared divided by g times the mass of the sun. And so you get Kepler's third law. And lastly, they're just comparing, I think, what's called the Ptolemaic view and the Copernican view. So before Kepler was around, long ago, there was an idea that the Earth was at the center of the universe and that all these things we see in the sky orbited around us. And it was a pretty complicated system. You had Mercury and Venus going in circles around their circular path, and Mars going around its path that allows it to go backwards, retrograde. And if you go to the Copernican view, where the sun is at the center of the solar system and the Earth is the third planet away from the sun, it offered a simpler explanation of the observations we made. And that's it for Chapter 6.